The question of how life began has captivated humanity for millennia. From ancient myths to modern science, we have grappled with the mystery of how inanimate matter transformed into the complex tapestry of life we see today. This transformation, known as abiogenesis, remains one of the most fundamental and challenging questions in science. At the heart of this mystery lies the concept of LUCA, the last universal common ancestor. LUCA is not a specific organism we have found fossilized in rock, but rather a theoretical construct. It represents the hypothetical ancestor of all life on Earth, a single-celled organism that lived billions of years ago in a hot, primordial world. Understanding how LUCA emerged from a lifeless planet is a daunting task. It requires us to peer back through billions of years, to a time when Earth was a very different place. Yet, despite the immense challenges, scientists are making remarkable progress in piecing together the story of life's origin. For centuries, the prevailing belief was that life arose through spontaneous generation, the idea that living organisms could emerge directly from non-living matter. This notion was finally put to rest in the 19th century through the work of scientists like Louis Pasteur. However, even as spontaneous generation was being debunked, other scientists were conducting experiments that hinted at the possibility of life arising from non-living matter through a more gradual process. Antoine Lavoisier's experiments in the 1780s demonstrated that both living organisms and burning coal released heat and carbon dioxide, suggesting similar chemical processes at play. In 1828, Friedrich Wöhler accidentally synthesized urea, an organic compound found in urine, from inorganic ammonium cyanate. This groundbreaking experiment challenged the long-held belief that organic compounds could only be produced by living organisms. It opened the door to the possibility that the building blocks of life could arise from non-living matter. One of the most enduring theories about life's origin is the primordial soup hypothesis. This theory proposes that early Earth was covered in shallow pools of water rich in organic molecules. These soups were energized by volcanic heat, lightning and ultraviolet radiation from the sun, creating a crucible for the formation of more complex molecules. In 1953, Stanley Miller and Harold Urey conducted a landmark experiment that simulated the conditions of early Earth. They filled a sealed flask with water, methane, ammonia, and hydrogen gas, and subjected it to electrical sparks to simulate lightning. Remarkably, after just a week, the flask contained amino acids, the building blocks of proteins, providing support for the primordial soup hypothesis. Another prominent theory is the RNA world hypothesis. This theory posits that RNA, not DNA, was the primary carrier of genetic information in early life. RNA is a simpler molecule than DNA and can both store genetic information and catalyze chemical reactions. Scientists believe that RNA may have played a crucial role in the emergence of life. Section 4. From protocells to LUCA, the dawn of cells. The emergence of cells marked a critical step in the origin of life. Cells provide a protective barrier from the environment, concentrate molecules, and create a stable internal environment where complex chemical reactions can occur. But how did the first cells arise? One possibility is that life began in hydrothermal vents, fissures in the ocean floor that release heat and chemicals from the Earth's interior. These vents provide a source of energy and nutrients, and some scientists believe they could have been the cradle of life. Another theory focuses on protocells, simple, membrane-bound structures that are considered precursors to modern cells. Protocells can form spontaneously under certain conditions and exhibit some characteristics of living organisms, such as the ability to grow and divide. Once protocells emerged, they would have been subject to the forces of natural selection. Those protocells that were better at replicating themselves and adapting to their environment would have been more likely to survive and pass on their traits. Over time, this process of evolution would have led to the emergence of LUCA, the common ancestor of all life on Earth. Section 5. The enduring mystery of life's origin. Despite significant advances in our understanding of abiogenesis, the origin of life remains one of the most challenging and captivating mysteries in science. While we have discovered many pieces of the puzzle, the complete picture is still being assembled. The theories and experiments discussed here provide a glimpse into the incredible journey that led from a lifeless planet to the rich tapestry of life we see today. As we continue to explore the cosmos and delve deeper into the secrets of biology, we move closer to unraveling the mystery of our own origins. The search for the origin of life is ultimately a search for ourselves. By understanding how life emerged from non-living matter, we gain a deeper appreciation for the interconnectedness of all living things and our place in the universe.